Filipino scientists and their game-changing contributions to the world of science. Know more about all of them and let the Salin Lahi Science Center be your gateway into their minds. Salin Lahi.
Reminded of our house rules. Proper decorum is expected among all participants. Any act of disrespect and rudeness shall not be tolerated throughout the duration of the webinar. Kindly key in your questions for the panelists in the Q&A. These will be answered during the open forum.
Good morning to everyone. I am Dr. Ivan Gue. I am the chairman of the Department of Mechanical Engineering of the La Salle University, and I will be your moderator for this focus group discussion. This focus group discussion will be on carbon dioxide removal with negative emission technologies, hosted by the Engineering Science and Technology Division of the National Academy of Science and Technology Philippines. Now, this forum aims to discuss the viability of integrating NETs into a multi-decade national climate change plan, and also to craft a white paper outlining the research, development, and deployment roadmap for NETs in the Philippines. To formally start our program, may we call on Academician Euphemio Rasco, the interim president of NAST, and member of the Agricultural Science Division, to give the welcoming remarks. Academician Rasco, the virtual floor is now yours.
Thank you very much for the kind introduction. National Scientist Dolores Ramirez, esteemed colleagues in the Academy, fellow workers in government, our invited resource persons, participants from the science community, and guests. Pleasant morning to all of you. On behalf of the Academy, I'm pleased to welcome you to today's focus group discussion on carbon dioxide removal. Today's discussion will focus on negative emission technologies. As the symbol of the nation's commitment to science, the National Academy of Science and Technology Philippines, an attached agency to the Department of Science and Technology, is mandated by law to serve as an advisor to the President and the Cabinet on policies concerning science and technology in the country. Through various activities, members of the Academy and other experts gathered here today to present up-to-date information and to raise awareness to the general public and put forward science-based policy recommendations to address the gaps and improve policy implementation to our policymakers. This FGD aims to present new technologies that will help lessen the effects of global warming and to tackle this issue as a whole, to achieve a healthier and more sustainable environment, and to draft appropriate policy recommendations. I expect the discussion to identify key factors in establishing carbon neutrality targets to be on track to meet its commitments in reducing greenhouse gas emissions. Negative emission technologies have the potential to be a viable contributor in lessening the effects of global warming. In particular, we hope to come up with policy recommendations that will address environmental concerns to reduce carbon emissions and develop negative emission technologies to achieve a sustainably cleaner and safer environment. I would like to thank the Engineering Sciences and Technology Division for initiating this event. Let me particularly acknowledge the efforts of academician Raymond Tan, who worked hard to make this event possible. I would also like to thank Engineer Maria Victoria Migo Sumagan, Dr. Beatriz Del Monte, Dr. Ivan Henderson Cue, and Dr. John Frederick Tapia for their participation in this focus group discussion. On behalf of the Academy, I would like to thank everyone for sharing your time with us, and I look forward to a meaningful and productive discussion with all of you. Once again, pleasant morning to all.
Thank you very much, Academician Rasco. Now, before we proceed with the discussion, let us now call on Academician Raymond Tan, member of the Engineering Sciences and Technology Division of NASD, to give us an overview of this focus group discussion and discuss negative emission technologies. Academician Tan is a distinguished professor of the Department of Chemical Engineering, a university fellow, and the current vice president for research and innovation at De La Salle University. He is also a member of NASD. He has close to 500 publications in the Scopus database with over 11,000 citations and an age index of 53. His research in systems engineering with applications to carbon management and industrial sustainability. And he is the co-developer of the carbon emission pinch analysis algorithm. He is the editor-in-chief of Process Integration and Optimization for Sustainability, associate editor of Sustainable Production and Consumption, and of Cleaner Engineering and Technology. He serves as an editorial board member of Clean Technologies and Environmental Policy. He has received multiple scientific awards and distinction and is included in both Stanford list of the top 2% of the world's scientists across all fields and the Reuters hot list of the world's top 1,000 climate researchers. Academician Tan, the virtual floor is now yours.
Thank you very much, Dr. Gue. To my colleagues, the national scientists in attendance, Academician Pasco, NAST interim president, members of the Academy, our resource persons and MC, and of course the NASD support team. Good morning. If you'll allow me to share my screen, I've prepared a brief presentation to give an overview of negative emissions technologies. I'll begin my presentation with this quote from an IPCC report that was published earlier this year. This is the AR6 report of Working Group 3. And one of the excerpts says that carbon dioxide removal will be needed to counterbalance residual emissions in the energy sector. And this authoritative statement actually points to the need at the global scale to be able to not just cut greenhouse gas emissions, but to actually do the reverse and remove carbon dioxide that is already in the atmosphere and draw it down into other environmental and physical compartments. So the overview that I'll be giving is broken down into 5 parts. The most important of which is a quick overview of negative emissions technologies and the role that we expect them to play in carbon management. Now, an overview here is based on the target to keep warming by the end of the century to well below 2 degrees Celsius of increase relative to pre-industrial temperatures, and aspirationally to get closer to 1.5 degrees Celsius. So that is the target zone. And that target actually requires very deep cuts in greenhouse gas emissions. And that actually means that if we look at current emissions that amount to 40 gigatons per year of greenhouse gases, that needs to be reduced to zero by the middle of the century. If you try to think of the scale of this task, that means that we need to reverse within the span of one human generation an increasing trend that goes back tens of thousands of years. So that is a pretty big challenge. Nevertheless, what we see globally is a zero emissions bandwagon. We have, for instance, the European Union committing to achieving climate or greenhouse gas neutrality by mid-century. Japan has done something similar. The UK has done that. And even developing countries like China and India and our neighbors in Southeast Asia have made pledges to achieve carbon neutrality, although much later than the developing countries, or rather the developed countries.
Where are you going?
We're going to go.
Now, what we also see is the need to achieve deep emissions cuts, not just using conventional technologies, but using techniques such as carbon capture and storage, also known as CCS, and carbon dioxide removal, or CDR techniques, otherwise known as negative emissions technologies. Now, to understand exactly what is needed, it's important to go back to the basics, and that means understanding the global carbon cycle. This is from an IPCC cartoon from 10 years ago, and it shows us the major carbon fluxes that occur among the different major compartments on the planet. That is terrestrial carbon stocks, ocean carbon stocks, and atmospheric carbon stocks. The problem generally arises from the disequilibrium that results from human activities. And what that means in particular is through our use of fossil fuels, humanity is taking carbon that was originally stored geologically in hydrocarbons. And through combustion, we're converting that into carbon dioxide, which is then transferred to the atmosphere. And the disequilibrium arises from this rate of transfer being so much faster than the geological rates that we observed in pre-industrial times. So there is a net transfer into the atmosphere, and that creates a warming effect known as the greenhouse effect. So how do we get this under control? Some of the measures we can take actually rely on amplification or magnification of some of the flows that we find favorable for managing climate change. So for example, the most obvious low-tech solution is afforestation, which is simply the creation of new forest land. Now, the logic here is very simple. We know that deforestation creates greenhouse gas emissions through what is known as land use change, or LUC. And it stands to reason then that creating new forest area or reversing deforestation then generates what we refer to as negative land use change, and that draws down through photosynthesis carbon dioxide from the atmosphere. Now, that is definitely one of the solutions that we should look ahead to, but there are constraints and problems ranging from, of course, land use or land requirements of human populations, nutrient requirements, as well as biodiversity risks that are posed, for instance, when we have too much of one particular species of trees in large managed plantations. Now, related to this is a technique known as soil carbon sequestration. Soil is home to a large global stock of carbon in the form of both living and dead biomass. So it is actually possible to change some of our practices, for instance, in agriculture, to encourage the sequestration of biomass from, for example, from crop residues, to store this in soil so that it's locked up rather than being transferred to the atmosphere. So this is a technique which is alternatively referred to under the umbrella term of natural climate solutions. It has its advantages, again, being low tech and relatively mature, but there are concerns about the lack of permanence of storage because the biomass can, of course, decay afterwards and release carbon again into the atmosphere. But that is still one of the solutions we can look ahead to. Now, related to soil carbon sequestration is an engineered augmentation of that. And that means basically, rather than using raw biomass, to store carbon in soil. If we carbonize the biomass, basically if we make charcoal and instead of burning the charcoal, we use it just like compost as a soil amendment agent, then what we do as a secondary effect is we store the relatively stable carbon in this char as carbon in soil. And this can be done, for example, in the context of agriculture. It can be done in marginal lands as well, but it is a supercharged form of soil carbon sequestration. Now, if you look at the non-photosynthetic avenues for negative emissions, one of the major ones that is a subject of significant global research interest is enhanced weathering. Weathering is simply the natural reaction that occurs between carbonic acid, which is rainwater plus the dissolved atmospheric CO2, which is a very weak acid, and that reacts with alkaline minerals, for example, silicates, and that can result in the sequestration of the carbon as dissolved bicarbonate ions that are carried by runoff water into the ocean. So that is a naturally occurring process. It is, of course, as we say, geologically slow, but there are ways to accelerate this process and engineer the systems so that we're able to capture this at significant rates for the global climate mitigation challenge. Related to enhanced weathering is ocean alkalinization. The ocean is a large sink for carbon, but the equilibrium between the atmosphere and the ocean, especially the surface waters, really depends on pH. And the more alkaline the ocean is, the more CO2 it can absorb through dissolution and through reactions. But the problem there, of course, is as the amount of CO2 in the atmosphere increases, more of it dissolves in the seas and actually raises the pH. So if we can synthetically, but of course, looking at the potential adverse effects on marine life, just very slightly raise the pH, that can enhance the absorption of CO2 from the atmosphere and just use the large potential of the ocean as a carbon stock. And of course, there are highly engineered techniques, for example, direct air capture, which uses chemical and physical processes to directly skim CO2 from the atmosphere, and the related technique of bioenergy with CCS, and that uses biomass that is cultivated to draw CO2 from the atmosphere and then used as fuel in large industrial plants. But rather than returning the exhaust gases from combustion into the atmosphere, we use chemical and physical processes to remove the CO2 and eventually find a geological sink in which to store the captured CO2 from both of these engineered techniques. The problem there is you need to have large and secure CO2 reservoirs to enable such long-term storage. So these are not the only techniques, but these are the major ones that are currently considered mainstream in the global net literature. Now, this is also not just science fiction, nor is it just laboratory work. There are actually startup companies being put up all over the world, particularly in the Middle East, in Europe, in North America, with the intent to commercialize some of these technologies. And what that bodes for the future is the potential to actually have companies that sell carbon credits from their negative emissions operations. And that can be traded, for example, across national boundaries. And the Philippines needs to be prepared for that, what we may refer to as a future carbon drawdown economy. Now, let me switch briefly to this sort of research that I've done in negative emissions. I work in an area known as process systems engineering. And in particular, I've developed an extensive body of work on carbon management networks using different computing techniques, which goes back to almost an initial work that dates back to 2005. And that has led to some significant accolades and recognition of the carbon management work being done in the Philippines, but on a global stage. including, for example, recognition by the Institution of Chemical Engineers in the United Kingdom for some of the work in carbon management. Since 2020, I've worked with colleagues both locally and in other parts of Asia and the European Union to consider how these computing techniques can be brought to bear on the problem of scaling up negative emissions technologies. And what we need to point out here is on a global scale, we're not talking about thousands of tons of CO2. We're not even talking about millions of tons. It needs to be in the billions of tons of CO2 for it to be significant in the global climate change mitigation efforts. And if we were to look at the Philippines, that needs to be in the millions of tons scale, or at least tens of millions of tons, for it to make a dent in our annual greenhouse gas emissions. And to scale this up to that level really presents significant engineering challenges. So let me just illustrate what that means. If we take enhanced weathering as an example, that is a technique where you take silicates, for example, a common rock such as basalt can be pulverized to the fineness of cornstarch, and you could actually apply that on agricultural land as shown on screen. Normally that's done for pH adjustment in the soil, but that actually, as we've seen, that captures CO2. And it's estimated that the potential globally runs into the billions of tons per year of CO2 emissions reduction. So that is significant. That's about 10% of global emissions at the moment. So it is significant from the global perspective. A year ago, I did a webinar on this, so you may want to listen in if you follow the QR code. But the problem you see is not just the chemistry and the physics of it, but when we scale this up to the point where we need millions of tons of CO2 to be captured, that means moving millions of tons of rocks from where the powder is produced. That means we take the rocks from the quarries, we grind it to a fine powder, and then distribute it to various application sites, which should be selected and optimized, for example, based on rainfall and other weather conditions. So in 2019, we created the first optimization model to address this issue. We've also applied other computing techniques such as pinch analysis, and we've considered alternative transportation modes, including aircraft, trains, pipelines, to be able to map out these carbon management networks, as we call them. So that's part of the engineering toolbox, which potentially can scale up these techniques to the point where it's significant. And we've worked with colleagues just not too far north from where we are in Taiwan. We looked at iron production waste, and we computed that in Taiwan, that potentially can capture 2 million tons per year of carbon dioxide just using one kind of industrial waste. And of course, working with colleagues from mainland China, we've seen that using various kinds of industrial waste just in one region, again, millions of tons potentially of CO2 emissions can be reduced or can be removed from the national inventory. But that still needs to be done in the Philippines. Now, as we proceed towards the end of this overview, I will give a bit of a preview of our panel. Dr. Bea Belmonte, who's with the University of Santo Tomas, has done extensive work dating back to 2016 when she was a PhD student on using biochar as a means to capture CO2 and to generate negative emissions, and within the context also of agricultural systems so that you get co-benefits from scaling this up. Next, engineer Migo Sumagan, who is currently in the finishing stages of her PhD, has worked on optimizing negative emissions portfolios, not just for the Philippines, but for Southeast Asia. And that means really, given the constraints of any region or country, if you have a set of options available to you before the investment decisions are made, we need computer models to figure out how best to put resources into this carbon dioxide removal enterprise. And this is why the work that she's been doing is dedicated to portfolio optimization. And Dr. John Frederick Tapia has worked recently on decision analysis techniques, again, not just for figuring out how individual negative emissions technologies perform, but if you had a list of options with different criteria and you don't know precisely how they might perform in the future, you would still need to make decisions as to which ones to prioritize for research and development, for deployment and such. And he's developed computing techniques to address these challenges. So as I proceed to the end of this orientation, these are the research issues that carbon dioxide removal presents for the local and for the global scientific communities. Number one is there is a bit of a climate emergency, and we need to scale up these techniques, but at the same time, they're subject to various technical and economic uncertainties. Then we need to identify possible unintended consequences and ripple effects, because there will always be strings attached and price to pay for scaling up even a seemingly innocuous technique such as afforestation. We need to contend with natural resource limitations, including land area, precipitation level, biodiversity concerns, and such. Next, negative emissions, of course, will be part of a larger carbon management strategy for any given region or country. And that includes, for instance, exploring non-fossil fuel-based electricity production, for instance, more renewables. Nuclear energy has been discussed in the context of the Philippines. And all of these techniques have to be part of a larger portfolio of climate change mitigation strategies. And then there are the soft issues, not just the physical sciences, but social acceptability, the legal and regulatory framework. Across national boundaries, we have the issue of geopolitics and climate justice. For instance, the ongoing discussion on to what extent should developing countries be responsible, or should we contribute to global efforts to reach net zero emissions? And the bottom line, of course, is the economics. CDR is not going to happen by itself. How do we put a price tag on this, and who pays for it? Do we put this on corporations, the citizens who benefit ultimately from CDR, governments? Of course, that is a discussion that needs to take place in the future. But in conclusion, I just want to make 3 points. If we look at the physics and the chemistry of greenhouse gas emissions, there is no doubt that negative emissions will be needed to achieve net zero by the middle of this century. We've seen and we've proven through recent work that models can help facilitate the rapid scale up of negative emissions technologies to the level that we need them within just a few decades. And these have implications for the Philippines, not just the rest of the world. Number one, a national carbon neutrality target needs to be discussed, it needs to be set. And this is really part of being in solidarity with the rest of the world based on managing our common atmosphere. Number two is the Philippines will need an optimized decarbonization roadmap to implement any such pledge that is made. So first is a top level target, and then the actual details of how to do it, which could include decarbonization of our electricity, but it will probably include some form of CDR through appropriate techniques. And thus, given the constraints of this country, given the development, given demographic and economic trends, then we need to identify viable net options and strategies so that these can be the subject of research, development, and policy decisions in the very near future. Thank you and good morning. I look forward to engaging all of you in deeper discussion later this morning.
Thank you, Emission Tan, for that overview. Now, at this point, we'll start with the panel discussion on the research and development of negative emission technologies. Our first panelist is Dr. Beatriz Belmonte. She is the assistant professor at the Chemical Engineering Department of the University of Santo Tomas. She graduated with a degree of Doctor of Philosophy in Chemical Engineering at De La Salle University She is also a scholar under the ERDT program of the Department of Science and Technology. Her work focuses on developing computer models, providing decision support for the use of carbonized biomass as a social enhancer and as a form of carbon sequestration. This strategy is regarded in the literature as a potentially effective way to reduce greenhouse gas emission. She also has done research among Scopus Index publication in major journals, which have received a combination of 126 citations, and her current Scopus H index score is 6. In addition, her paper optimization-based decision support methodology for the synthesis of negative emissions biochar systems has been globally recognized and listed among the 31 publications featured in the UK IChemE Climate Change Collection last June 2020. She was one of the 25 accepted scholars among 210 applicants that attended the 2020 Southeast Asia International Joint Research and Training Program on Low Carbon and Energy held at National Tsinghua University. She was awarded the Best Scientific Poster Award during the NASC 42nd Annual Scientific Meeting last July 2020. She is a member of the editorial board of Carbon Research. She is also a reviewer of Sustainable Chemical Process Design, Journal of Cleaner Production, Biochar, Education for Chemical Engineers, and Clean Technologies and Environmental Policy. She has recently been elected as a full member of the Philippine American Academy of Science and Engineering. She is also a regular member and presently serves as the secretary of the NRCP Division of Engineering and Industrial Research. She teaches at the Faculty of Engineering and is also a resident researcher at the Research Center for the Natural and Applied Sciences of the University of Santo Tomas. Dr. Belmonte, the virtual floor is now yours.
Thank you very much for the very nice introduction. I would like to thank NAS for inviting me in this forum on negative emission technology. So again, good morning, everyone. My presentation for today focuses on the role of biochar in climate change mitigation and how it can be implemented on a large-scale basis with the aid of mathematical modeling. My presentation is divided into 4 parts as shown. I will begin with a brief introduction about the recent climate information and large-scale biochar-based carbon sequestration as a negative emission strategy to address climate change. Then I will continue to discuss the modeling framework I developed for biochar-based carbon management networks, which includes some results of the case studies. I will end my presentation with a conclusion and prospects for future work. I will also show some of my papers for further readings. Let me begin with the introduction. It is well known that climate change is one of the major environmental crises that the world is facing. And the recent information on climate reveals that carbon dioxide emissions are rapidly recovering after a temporary deviation from its normal trend due to the economic slowdown caused by the pandemic. And greenhouse gas concentrations in the atmosphere continue at record levels, and we are still significantly off schedule to meet the goals of the Paris Agreement. And considering that time is running out and climate impacts are becoming inescapable, there is a need for all countries to commit to net zero emissions by 2050. And ultimately, one of the biggest incentives for major economies to tackle this climate crisis is to avoid the long-term impacts or costs associated with its impacts. It is quite remarkable that in European Union, 27 countries have agreed last year on the first ever European Union climate law, which means that they are all binding themselves to becoming climate neutral by 2030. This is a legal obligation for the 27 member states of the European Union. China as well has pledged to reach net zero emissions by 2050, and all major multinational corporations such as Nestle have also committed to zero emissions by 2050. It is a good thing that a political framework has been set to significantly reduce carbon emissions, The next challenge is engineering the carbon drawdown. There is a need for the deployment of these technologies as shown to meet the targets of the Paris Agreement. And negative emission technologies have received substantial attention, and ample papers have been published since 2018, which provide qualitative and quantitative assessment of their potential in climate mitigation. Negative emissions from biochar application to land has fewer disadvantages compared to other negative emission technologies and can potentially reduce emissions by around 0.9 to 3 gigatons of carbon dioxide per year. But how can biochar help mitigate climate change? Of course, we all know that carbon can be stored in soil as crop residues or humus, but crop residues usually oxidize into carbon dioxide and are released into the atmosphere within a couple of years. And the lifetime of carbon in humus is typically less than 25 years. When the biomass is instead pyrolyzed, a stable solid product is produced that largely consists of a recalcitrant carbon fraction with a half-life of a few centuries in soil. And the carbon-rich product is called biochar when it is stored below the ground for long-term removal of atmospheric carbon. Direct sequestration in biochar coupled with beneficial secondary effects can potentially mitigate 130 gigatons carbon over the course of the century. And this is obviously an amount that can significantly contribute in achieving net zero emissions by 2050. However, there are implications that we also need to look, such as land, water, and nutrient footprints that come with the climate benefits during its large-scale deployment. There may also be adverse impacts. Biochar is naturally alkaline and contains macronutrients and, unfortunately, potential contaminants. Now, the potential release of these contaminants is possible since biochars are often prepared from a variety of feedstocks, including waste materials. And putting too much biochar in soil may affect soil quality. Unexpected drawbacks may occur, such as release of potential contaminants present in biochar, oversupply of nutrients, and excessive increase in soil pH. Now, having in mind the promising benefits and unintended consequences of biochar application to soil, how can we optimally deploy biochar to maximize the benefits and overcome potential disadvantages? There will surely be a need for an important toolbox that we can use. Process systems engineering can aid in the development of a modeling framework to support decisions for a specific type of problem. Now, these papers are shown discuss the emerging role of process systems engineering in the proper deployment of biochar-based carbon management networks. Computer-aided planning of biochar-based carbon management networks will be needed to maximize greenhouse gas reductions while minimizing any potential adverse environmental impacts. And these models can help decision makers to understand and optimize the cost-benefit aspect of such systems to accelerate their commercial deployment. Let us now move on to the modeling framework I developed. The promising results of biochar application to soil can be potentially optimized through biochar-based carbon management networks with the aid of mathematical programming. And in this work, the term biochar-based carbon management networks is proposed to describe systems that are intended to strategically plan carbon sequestration via systematic production and allocation of biochars for long-term storage to agricultural lands, and of course to simultaneously improve soil properties. This study develops an optimization framework for biochar-based carbon management networks by accounting for relevant and practical aspects of biochar research as shown. This work is the first to integrate these aspects of biochar research into a systematic framework for the high-level planning of large-scale biochar-based carbon management networks. Let us start with the optimization model I developed for biochar-based carbon management networks. The first phase is the development of an optimization model for biochar-based carbon management networks. An objective MILP model is developed for the synthesis of biochar networks with profit and carbon sequestration as the objective functions, and the model calculates the optimum allocation of biochar such that their prescribed limits for the contaminants are met, since I mentioned a while ago that biochar can contain potential contaminants. Also, different variables, parameters, and constraints incorporated to account for the incompatibilities of biochar sources and sinks, and to allow for control of biochar characteristics so that biochar can be customized to address specific soil quality requirements. The illustrative case study clearly demonstrates the applicability of the model, and a case study is given here that represents Central Luzon region in the Philippines. The semi-hypothetical case study depicts 3 biochar sources, 4 biochar sinks, and a time frame of 10 years, or operational time of 10 years. Let us now discuss some results. The trade-off between carbon sequestration and profitability is depicted in the figure, and each point here corresponds to a particular biochar sourcing network. Let us choose a representative example, say Network A. The table gives the optimum amount of biochar allocated for each sink coming from each source in the network. The first and second values in each cell show that the biochar allocation during the first 2 years and last 8 years of operation, respectively. And the model recommends blending of low and high grade biochar at sink 3 during the 10-year time frame so as not to exceed the limit prescribed for the contaminant. And as you can see here, 919 grams per ton is less than 1,500 grams per ton of sodium, which is the limit prescribed for sodium in sink 3. Now, the effect of pyrolysis temperature on carbon sequestration and profitability is also investigated, and the figure shows the trade-off between carbon sequestration and profitability for the different values of pyrolysis temperature. And it can be seen in the figure that as the temperature decreases, the system-wide net carbon sequestration and profitability increases. Let us again choose a representative example, say Network A. The result of Network A is shown in the table. And every sink has distinct soil quality characteristics, and biochar can be customized in order to fit certain soil conditions. And for instance, the amount of contaminant, nutrients, as well as the level of alkalinity in biochar can vary depending on the pyrolysis temperature in which the biochar is to be produced. For example, the quantity of phosphorus nutrient applied to sink 3 at 300 degrees Celsius is 5,317 kilograms per year during the final 8 years of operation, which is within the range of phosphorus application rate for sink 3. Now, the generation of near-optimal solutions are then conducted in the second phase of the study. The generation of near-optimal solutions emerges as a significant paradigm for systems synthesis, and decision makers are likely to favor such an approach over the analysis of a single optimal solution, given the uncertainty of the planning process. Near-optimal solutions or alternative allocation networks are generated by addition of integer cut constraints in the original mathematical problem formulation, and such near-optimal solutions are important for practical decision-making because these near-optimal solutions can be tested for robustness amidst variation in biochar supply due to various factors that may arise, such as changes in agricultural productivity. And the information gathered is analyzed to select a network for actual implementation. And since uncertainty in the supply capability of the sources can exist, the different networks generated were then tested for robustness using Monte Carlo simulation. And a given network is said to fail if the excess supply capacity of any source becomes negative. That is, if the system incurs any biochar supply needs. The summary of the results is shown in the table. It can be seen that the optimal network will experience a high probability of failure. This result means that even though the optimization was designed to be conservative, by assuming the lower estimate for the supply capabilities of the sources, there is still a 22.9% chance that source 2 will not be able to meet the target allocations for the sinks based on the design. And likewise, there is also a 17.8% chance that source 3 will not be able to meet the target allocation for the sink based on the design. However, alternatively, suboptimal networks 1, 2, and 3 were much less likely to fail, with probabilities of incurring supply deficit of not more than 3.2%. In the third phase, an optimization model for the biochar sources was developed. This phase of the study dealt with the production of customized biochars to address specific soil quality limitations. And this is a novel application area of process systems engineering research that is also addressed in this work. This phase of the study demonstrates the synthesis of polygeneration energy system that produces different grades of biochar alongside the energy products for profit maximization. And as you can see in the figure, 3 pyrolysis units that generate biochars with different specifications are integrated in the system. And the resulting multi-grade biochars can address specific soil quality requirements. The figure shows the polygeneration plant flow sheet for the case study. This table shows the proposed framework for matching different grades of biochar produced from the polygeneration system to amend specific soil property, and the type of soil and the type of designer biochar suitable to amend specific soil property are indicated. For example, if the type of soil is acidic, then the soil property that needed modification is soil pH. And if the biomass that will be used to produce biochar is rice husk pyrolyzed at 600 degrees Celsius, then this rice husk biochar can increase soil pH. The corresponding configuration of the optimized polygeneration system is given in the figure, and as can be seen, the steam or water heat exchanger is excluded in the optimal solution. The outputs of the polygeneration system are shown, specifically the different grades of biochar. Now, the generated near optimal solutions are presented alongside the optimal solution in the table. And the installation of the 3 pyrolysis units in all solutions results in a carbon footprint of negative 65.84 kilogram per second or 1.9 megatons of carbon dioxide per year due to the production of biochar. And meanwhile, it is notable to mention that the fourth best solution is only 0.6% lower in profit compared to the optimal solution, and the complexity is lessened with the exclusion of hot water generator and electric chiller. Again, this result demonstrates that minimal differences may not yield significant implication, so that the selection of the solution for final implementation may be based from other criteria that have not been counted in the mathematical model. For the conclusions and prospect for future work, a novel framework has been developed that provides a sustainable strategy to aid the proper deployment of biochar-based carbon management networks to contribute to climate mitigation. It generates useful insights that can guide policymaking, such as incentivization of commercial-scale biochar-based carbon management networks. The framework is comprised of component mathematical models that capture the salient features of biochar research as currently envisioned in the literature. And looking at the bigger picture, this work can serve as the core for the development of more complex formulations in the future as the state of knowledge evolves. Future work can focus on novel data acquisition methods for the sources and sinks. For further readings, this is my recent published book chapter. Here is our recent publication, a suggested reading. This paper was recently submitted to Artificial Intelligence Journal and is currently under review. This paper developed a rule-based model for the prediction of changes in soil greenhouse gas fluxes due to biochar application with the aid of rough set-based machine learning. Thank you very much for your attention.
Thank you very much, Dr. Del Monte. Next, to share our insights is our second invited panelist, Engineer Maria Victoria Migo Sumagang. Engineer Migo Sumagang is an assistant professor at the University of the Philippines, Los Baños. She is a recipient of the Academic Achievement Award during her master's in chemical engineering degree from UPLB and the ERDT PhD scholarship at the La Salle University. She is a registered associate ASEAN engineer and an associate member of the National Research Council of the Philippines. She has published peer-reviewed journals on rice straw for bioenergy and its life cycle assessment, as well as co-authored book chapters on sustainable rice straw management. Her current research involves the application of process integration to negative emission technologies portfolio for a systems-level outlook on these technologies. She has published peer-reviewed journals on this topic and co-authored a correspondence article in Nature Computational Science about computing optimal NET portfolios. She currently has a total of 205 citations with an H index of 8. She was awarded multiple best posters and best presentations for her research on NET portfolios. Engineer Migo Sumagang, the virtual floor is now yours.
Good morning, everyone. Thank you for the introduction. Let me share my screen. Okay, I'm Maria Victoria Migo Sumagang, and I will share my research on NETs, or sometimes I call it NETs for short, particularly on multi-footprint optimization of net portfolios. As Professor Tan mentioned, part of the climate change mitigation should come from nets. And I just want to emphasize that there are two motivations behind nets. One is biophysical and the other is economical. Biophysical, because the conventional approaches are not enough. We are way past the point wherein we can reach net zero emissions by conventional approaches alone. Economical, because immediate and full decarbonization will also be unlikely. Recently, we had the COP26, or the Glasgow Climate Pact, and the term that they used is phasing down rather than phasing out coal, especially for the growing markets of China and India. Hence, nets will be needed to remove the residual emissions, especially in the energy sector. In fact, the recent IPCC report in 2022, just this year, officially included nets in the list of strategies. And they stated, as Professor Tan mentioned, that nets are needed to counterbalance the hard-to-abate emissions from the difficult-to decarbonize industries, including aviation, heavy transport, even agricultural, steel, and cement industries. But what are the challenges in implementing large-scale nets? Nets have different features. They have environmental footprints and will consume resources such as land, water, energy, nutrients, and even budget to deliver negative emissions. In large scales, they can even exceed the planetary boundaries. These are the recommended safe operating space for land use, water use, etc. Biomass-based nets like afforestation and BECCS have wide-ranging effects on biogeochemical cycles, and the mismanagement and poor implementation of these nets may impact the water quality, food production, biodiversity, and even livelihoods. Nets have temporal limitations as well. They vary in technological readiness, or the time when the technology will be ready for implementation. Some technologies can be implemented earlier, like afforestation and soil carbon sequestration, but some will be scaled up by mid-century, like direct air capture. But the deployment of nets is urgent. Facilities also have lifespans and operating hours. Biological nets have sink saturation, like when forests reach their maturity and they stop absorbing carbon dioxide. Nets also have either trade-offs or synergistic interactions. So synergistic interactions when they consume fewer resources when implemented together. For example, the application of biochar and enhanced weathering rocks on the same site may share the supply chain and may have a positive impact on the cost. They may also be applied to the land growing biomass so that they consume less fertilizer because they can act as soil enhancers. Emerging technologies such as direct air capture are subject to uncertainties in performance and cost. And because no single net can sustainably deliver the required negative emissions, net portfolios at smaller scales are needed. So to consider all of these aspects in the large-scale deployment, there is a need to simulate, optimize, design, select, and rank nets, whether individually or as a portfolio. Process systems engineering can support the designing and planning of net systems, and studies on nets under this framework are available in the literature. Here are some of the process system engineering works on nets, including the works of Dr. Belmonte, Dr. Tapia, and Professor Tan. So some techniques, various techniques such as pinch analysis, mathematical programming, and p-graphs have been applied to nets since 2013. And most of these studies have focused on the cost and carbon footprint optimization and not the multi-footprint optimization. And consideration of time aspects is also very rare. Similar with integrated assessment models, these technologies are implemented separately rather than in combination or in portfolios. And this is where my research fills in the knowledge gap. The aim of my research is to develop multi-footprint optimization models using process system engineering techniques for the large-scale deployment of net portfolios, considering multi-footprints, temporal constraints, synergies, and uncertainties, or the aspects that I mentioned earlier. And since there is a time aspect, discount rates for both economic and carbon value were also considered. The output of this work are optimum net portfolios throughout the 21st century. The next slides will show the research dissemination that we did so far on nets. The first one is a single period model that minimizes the cost of a nets portfolio while meeting a target negative emissions and resource constraints using global scale data. We also did a sensitivity analysis. One interesting observation is that, let me zoom in on this part. As the target negative emission is increased, the portfolio shifts from just having biochar and enhanced weathering to including direct air capture. And the extent of direct air capture needed increases as the target negative emissions increases. So by the way, if you are interested in any of these papers, I included the link and the QR code, and so far all of these are open access. The next one is interesting as well. This time we considered synergistic interactions in the optimization model using ASEAN data. And this study has shown that considering the synergies in the cost and land use resulted in better solutions in the sense that there is a higher negative emissions potential at lower cost or lower land use. So the previous two papers I showed used mathematical programming as the technique in the optimization. The current slide uses a graphical technique called the marginal abatement cost or MAC curves, and they involve plotting multiple mitigation options on rectangular coordinates with cumulative abatement as the horizontal axis and marginal abatement cost as the vertical axis. The options are arranged in increasing MAC such that for any given marginal threshold, the corresponding cumulative abatement that meet the threshold can be readily determined and easily communicated to decision makers. But for this paper, we replaced the cost with environmental footprints, such as land use in this case, but using the same concept as MAC curves. The publication for this work will be released in December this year. We also presented a multi-period model as a poster entry in this year's NAST scientific poster session, this time considering time constraints. I put the link and the QR code if you're interested to view the poster in detail. But probably the most interesting study for this forum is the preliminary Philippine case study that we presented in the PAASE APAMS this year. The Philippines may benefit from negative emissions due to our economic and energy growth. We are also rich in agricultural and forest residues, which can serve as feedstock for biochar and BECCS. And in terms of geological storage, we have over 23 gigatons carbon dioxide storage capacity available in our saline aquifers. Another option is using alkaline wastes as a byproduct from industry or mining wastes for enhanced weathering. One barrier, though, is that for energy-intensive nets, they have to use renewable energy to ensure net negative emissions. However, the Philippines have currently limited renewable energy. Preliminary results show that a positive net present value is obtained when we put a price on carbon. And the Philippines may benefit when the more technological ready and cheaper options like afforestation, reforestation, and biochar are deployed immediately, while the less technologically ready and energy intensive options like enhanced weathering and direct air capture are deployed in the near future. So this is just a preliminary study. We need more Philippine-specific data for the footprints, costs, and resource constraints. Let me quickly share this slide about the ASEAN Net Zero commitment. For Southeast Asia, 8 out of 10 countries have net zero targets, excluding Myanmar and the Philippines. Our current commitment is a 75% conditional reduction in our business as usual emissions, and we have not yet committed to net zero emissions. In any case, the country may benefit from negative emission technologies. And I mentioned about putting a price on carbon. The current US carbon price is around $51 per ton carbon dioxide, but it varies from region to region. For example, in the European Union, they have a different carbon price. So to give you a picture of what is happening today, many companies are targeting net zero emissions, and one way they do this is by buying offsets, some of which come from negative emissions, most popularly through afforestation and reforestation projects, but more and more companies are investing in direct air capture projects. So there is already a market for this, companies that are buying and selling carbon credits, and independent companies that are verifying these carbon credits. Using nets and starting a carbon market may open opportunities for the Philippines to trade carbon internationally as offsets and credits. However, strong policies are needed to ensure that there is a true environmental benefit from all of these activities. To summarize and conclude, nets can be used to biophysically and economically achieve net zero. The large-scale implementation of nets is challenged by multi-footprints, time constraints, uncertainties, trade-offs, and synergies. My research is the application of process systems engineering techniques to nets portfolios for a systems-level outlook on these technologies. Any initial results using global and ASEAN scale were disseminated in the literature. A preliminary Philippine case study was conducted. The country may benefit from negative emissions, but more Philippine-specific data is needed, and strong policies are needed to ensure true environmental benefit. Thank you very much to NAST for this opportunity. Comments and questions are welcome, or you may also email me to this email address.
Thank you very much, Engineer Miko Sumaga. Now for our next and last panelist, may we now call Dr. John Frederick Tapia. Dr. Tapia is an associate professor in the Chemical Engineering Department of the LaSalle University. He is a graduate of PhD in Chemical Engineering at the LaSalle University and had a postdoctoral research in University of Bath from 2018 to 2019. He was an ERDT scholar from 2012 to 2017. As an early career researcher, his research interests include process systems engineering for low carbon energy systems, mathematical modeling of biomass value chains, specifically oil palm value chain, and geographical information system-based analysis of suitable lands for oil palm. His expertise is on applications of nutrosophic sets in process systems engineering and decision analysis, specifically on data envelopment analysis and mathematical programming for process synthesis. He was awarded as one of the outstanding young scientists in 2022 in the field of chemical engineering. Currently, he has 37 Scopus Index published works with an H index of 12. Dr. Tapia, the virtual floor is now yours.
Hey, thank you very much, Ivan, for that introduction. Let me share my screen. Okay, so, well, many of the introductions are already provided by the two panelists and Professor Tan earlier. So my presentation would just be mainly on my work, specifically on ranking, evaluating, and selection of negative emissions technologies using a novel technique we call nutrosophic data envelopment analysis. So this paper was actually, or this method was actually developed around 20 late 2019. Then the work was published around late 2020. So to give you an overview of what I will be discussing, it's really about the negative different technologies, specifically the nets, in which they are ranked, selected, and evaluated based on the method of data envelopment analysis. So this is actually the paper actually presents a novel framework for modeling the uncertainties, and it also proposes a new method based on data envelopment analysis. And then finally, the selection was applied to negative emissions technologies. So this actually gave insight on which technology can be preferred more than the other, depending on how the expert perceive risk in terms of the selection. So the ranking might change from one expert to another, but the results actually prove that there are certain negative emission technologies here that are more flexible or more preferred at a certain range of risk behavior. So in this study, I technically applied or ranked or select and evaluated 6 negative emissions technologies. So what are the nets for evaluation? Well, to give you an idea on how the decision framework was done, there are 6 negative emissions technologies that were used to rank here. One is the direct air capture technology, bioenergy with CCS, afforestation, reforestation, soil carbon technology, soil carbon sequestration, biochar, and enhanced weathering, all of which were discussed earlier. And the decision is actually divided into 2 sets of criteria. The first one is the criteria that we prefer to be as low as possible, like environmental impacts and cost, while the other set is something that we prefer to be as high as possible, like readiness level or potential capacity. And with this kind of criteria, we will be able to apply what we call a data envelopment analysis. So the framework actually uses or aggregates the output criteria by finding a set of optimal weights in which the aggregated output divided by the aggregated input is what we call the technical efficiency. So in a classical approach in data envelopment analysis, the technical efficiency is maximized subject to each of the negative or each of the other technologies must have a technical efficiency of no more than 1. So the approach maximizes the weights or finds a set of weights subject to no technical efficiency should be more than 1. And the data envelopment analysis approach is an optimization framework performed for each of the technology. Then this is extended, or the input and the output criteria was extended to something like the inputs and the outputs are what we call nutrosophic in nature. So to explain it briefly, for inputs we want it to be as low as possible. So in this case, the satisfaction decreases as the input level increases, and the reverse happens to the output, where it increases as the satisfaction increases as the output levels increases. But there's also another component of nutrosophic sets, what we call the dissatisfaction, wherein it increases as input level increases and the reverse for the output. Now, in this case, it represents something that that can be adjusted, in which at a certain possible or a range of possible input levels, a certain expert may be a bit or maybe a bit more satisfied at a certain at a higher value, meaning even if he is totally unsatisfied at the uppermost level, or if the satisfaction is very low at a higher level, the dissatisfaction is somewhat decoupled from that of the satisfaction level. And the third component is actually the degree of attainability or uncertainty whether this level can be achieved. So the higher or the more efficient it is assumed that it's harder to achieve. So incorporating those considerations makes up the nutrosophic data envelopment analysis. And there are two parameters here, the tolerance for dissatisfaction and tolerance for indeterminacy, that can be adjusted depending on the expert level of perception to risk. And so applying the tool from in different risk tolerance level, changing from one decision environment to another, we actually produce this result in the stable. So if we just have a fuzzy data envelopment analysis tool, we cannot really differentiate the performance, because each of these technologies has its own advantages over the other. Or say, for example, DAC might be a much higher cost, but some other technologies can be of high land footprint. So we cannot really differentiate at this kind of decision environment. However, as it progresses, there is a certain preference of one technology than the other. Like direct air capture is really stands out at a intuitionistic fuzzy approach, while it becomes at the lowest part of the lower rank at the a completely nutrosophic or decision environment wherein the expert are not tolerant with the risk. So in that case, we can perform sensitivity analysis by varying the risk parameters, and then we will be able to produce different results at different risk parameters. In that case, we will be able to characterize or evaluate different technologies based on their response. For the data that we have for the using the tool, one of the general insights we can have here is that direct air capture by energy with CCS and afforestation are quite a good option because of their robustness or robustness in terms of their technical efficiency at different risk levels. And so with the sensitivity analysis, these are the insights that we have. DAC is efficient if policymakers would encourage to improve that technology perfectly as demonstrated in the tool. Then there are other options which has robustness or the ranking are on the top half of the six technologies. And these are BECCS, soil carbon sequestration, and afforestation. And in that case, it shows robustness in terms of ranking at varying risk perceptions. Biochar also needs to improve, but considering the three elements, it is better than what TAC, direct air capture, as shown in this table. And finally, enhanced weathering needs to be improved so that it would be more competitive than the other. So, well, for this paper, I developed a tool which is first applied on negative emissions technologies, and the results reveal different responses of nets in terms of ranking, depending on how the expert perceives the risk under it. So let me go back to my second slide here, which if you want to know the details of the work, you can find it on from this link, or you can actually scan this QR code. And that's it for my presentation. If you have further questions after this forum, you're encouraged to send me an email to this email address. Thank you very much.
Thank you, Dr. Tapia. Okay, now we will now proceed to our open forum. So if you have any queries or questions, you may post them in the Q&A portion. May we ask all our panelists to open their cameras? Now, to start the discussion on the open forum, maybe we could start with a few questions first. The first question is it viable and just for the Philippines to make a net zero pledge? And what will be the implications of such a pledge to the local R&D priorities?
Well, I think it's viable for the Philippines to commit to net zero emissions by 2050. I could speak in terms of biochar systems. The upper limit potential or sequestration potential of biochar is around 44 megatons carbon dioxide per year. This is equivalent to about 1/3 of Philippine greenhouse gas emissions. Now, this value is, I think, significant if we are talking about commitment to net zero emissions. But I think biochar alone could not solve the problem. There is a need to employ also other low carbon technologies and to decarbonize the transportation and power sector. But technically speaking, I think yes, it's feasible for the Philippines to commit to net zero emissions, but there is implication. There is a need for a lot of investment, you know? And I think it's now the implications for I think it will encourage or increase researchers that are deemed towards climate mitigation strategies. However, I think the government should increase the budget or financial support for these researchers so as not to affect the budget allocations for other research areas, which are also equally important.
Thank you, Dr. Belmonte. Yes, Engineer Migos Magam.
For the first part of the question, a net zero pledge is viable with the aid of negative emission technologies. This is because there should be a transition period for the Philippines to ease out fossil fuels. And during this period, we can utilize nets. In terms of technology viability, nets are viable, especially the low technology ones. We are already implementing afforestation through our national greening program. The next step for that is accounting for the negative emissions from that project. And biochar is being implemented in other countries, not just as soil enhancer, but also for asphalt and construction material additive. Direct air capture projects are also being implemented in other countries. So for that, we can do technology transfer or start our own direct air capture research. As for the second part of the question, whether it's just for the Philippines to pledge net zero when bulk of the existing carbon dioxide in the atmosphere were released in the past by industrialized nations. To me, the question right now is not whether it's just for the Philippines or not to pledge net zero emissions. The Philippines is one of the most impacted by climate change, although it's true that we are the least at fault, but not repeating the mistakes of the past and focusing on acting right now should be the priority, and that's the reason why we should pledge net zero emissions.
Thank you. And Jeremy Gosamaga.
May I add? Well, as far as I remember before, when one of the commitments made by the Philippines to as part of the INDC of the Philippines to the Paris Agreement, that we actually pledged a 70% reduction in CO2 emission, and it was later had to be reviewed. And I think, as far as I remember, NAST was involved in reviewing or revisiting our INDC, and it was one of the results or findings is that if we consider the development or the economic state of the Philippines back then, the most or the best actually is around 30 to 40%. But to answer the question, I believe that as time goes by, many information or more information are available regarding different technologies. Technologies become more ready for deployment. So I believe maybe in 2050, the Philippines can pledge or can it's possible to pledge on the net zero emissions by putting or by investing on technologies that we can possibly or we can implement or by putting investments on the best technologies that we can implement. So yeah, just to add to the answers by Engineer Sumagang and Belmonte.
Thank you, Dr. Tapia.
And also to add also, no, yes, it's fair for the Philippines to commit to net zero emissions, even though we are not the major emitter of greenhouse gases, no, as compared to China and the US. Because climate impacts will eventually affect also the Philippines. And after all, there's no boundary in the atmosphere. Every country will benefit from these climate change mitigation efforts. And so it is our moral obligation to take a share, to partake into this worldwide effort of achieving the negative or net zero emissions by 2050.
Okay, thank you, Dr. Taylor. Okay, maybe to extend on that question, what do you think are the essential components for a local carbon drawdown economy to develop?
Well, I could speak in terms of biochar-based carbon management networks. For the commercial implementation of biochar-based carbon management networks, there are players. No, there are multiple autonomous agents, which are the biochar source owners and the biochar sink owners. So these two are major components of a biochar-based carbon management network that are motivated to increase their own profit. And so I think on the other note, in order to implement these biochar-based carbon management networks, there is a need for the government to devise an effective carbon trading scheme so that both players, producers and owners could benefit from this strategy. But one implication is, of course, there is a need for investment on this type of projects. And I think the generation of carbon emission credits or certified emission credits will somehow offset the investment costs in this project and somehow will pull down the cost of biochar so that the farmers, who are ultimate users of this biochar, could afford the price. So I think it's really important to consider this aspect. Another is the validation, verification, and quantification of this certified emission reduction. So there is a need for an agent that will validate the actual climate change mitigation benefits from these carbon credits.
To add to what Dr. Belmonte mentioned, to me, I think the first step is putting a price on carbon, just like what is being done in other countries. This would entice startups to venture into negative emission technologies. There will be sellers of carbon credits and buyers of carbon credits. And of course, it's important to have an independent verifier of carbon credits.
Yeah. Also, to add, actually, when Ria mentioned about the putting the price of carbon, and we can actually utilize what our or what some of the academics are doing. Like, for example, research on game theory allows us to put a proper price on carbon, so that there would be a um, somewhat a cooperation or a synergy between the industry and then the government when it comes to um, developing policies for decreasing CO2 emissions and um, encouraging investments on NETs. And as for what Dr. Belmonte has mentioned on the biochar, I think one of the approaches that we can do here is to properly identify land areas that are best when it comes to application of biochar.
Okay, thank you. So I got a question here. As a fellow engineer, materials are always a big factor in developing technologies like NPs. May I ask, what are the other efficient alternative materials other than biochar that is viable here in the Philippines?
We can also utilize industrial alkaline waste from industry as well as mining waste. So these materials can also uh, absorb carbon dioxide through enhanced weathering.
Yes, Dr. Belmonte, would you like to add? Oh.
Yeah, actually, I did also study on the combination of biochar and these silicate materials in order to reduce carbon dioxide emissions. And there is, I think, a big possibility that the combination of these two technologies can be very much helpful to mitigate climate change. But again, there are implications because we also need to determine, the type of soil wherein these materials will be applied. It's very important to determine the characteristics of the soil, the pH, what are the soil quality requirements and limitations, because we need to design the appropriate type of biochar or silicate materials that would be applied in the soil. So that is an implication that we need to look at before we can apply these materials into the soil.
I would like to add to that. It's also important to study the toxic effects, since if we're going to use industrial alkaline waste and mining waste, so I'm sure that they contain toxic materials. So one research area that we should look into is the study of its toxic effects.
Okay, thank you, Jeremy Gasumaga and Dr. Belmonte. Okay, some more questions. By the way, despite the efforts the Philippine government makes through its attached agencies as well as other institutions to combat climate change by reducing carbon footprint in the atmosphere, the Philippines is still highly dependent on coal-based power plants. So when are we going to discuss other alternatives and science-based technologies, for instance, nuclear energy? Is the situation we are currently in not enough to adopt this technology? Is the science not enough to include this in our discussion? Thank you for your time.
Rather than nuclear energy, I would like to discuss solar energy because I recently attended a conference. Dr. Joey Ocon from UP Diliman made a model about the transitioning the Philippines into renewable energy, and they found out that it can be done through solar power. But of course, like what I have mentioned in the presentation, during the transition, and it's not enough to only use the conventional strategies. So there should be negative emission technologies, because once we exceed our carbon budget, no amount of renewable energy or conventional approach can negate the effects of the carbon that we already released in the atmosphere. So, but for nuclear, right now, I have no comment on that. But for renewable energy, I think based on the model that was presented in that conference, the one is solar energy. I mean, it's the best option based on the model.
Right. Yeah, perhaps it's time for me to comment because I've seen quite a number of questions already on nuclear energy, which is definitely one of the decarbonization options that the Philippines needs to consider carefully. However, NASD has already held events to discuss the issue of nuclear energy, and our event today is actually intended to address other avenues which have not yet been previously discussed. So in the interest of saving time, we will be addressing questions which have not yet been dealt with in previous NASD events.
Thank you, Academic Shantan, for that clarification, and Engineer Miko Samaga for that answer. So another question is, would it be sensible to focus on natural resources, or at least those made mostly from natural materials as substrate for NETs, like as material for direct air capture instead of those based on synthetics? Can you comment on the current economic viability of the current available NETs? Are there available evaluations of the NETs currently being developed by local scientists?
Yeah, perhaps, and again, let me chime in a bit here because I was involved in an Asian Development Bank project about 12 or 13 years ago. And when we have the engineered NETs, such as DAC, that's direct air capture, or bioenergy with CCS, an essential component of such systems is the presence of secure geological reservoirs, where you take your captured CO2 and you put it in the reservoir and basically assume that it gets locked up for geological time spans. Unfortunately, what we found more than a decade ago is because of our seismically unfortunate location in the Pacific Ring of Fire, there are precious few geological reservoirs that suit those conditions in this part of the world. The only exception is the western part of the Philippines, which is attached to the mainland Asia tectonic plate. That's west of Palawan. So that actually, to my mind, that shows that the prospects for bioenergy with CCS and direct air capture in most of the Philippines is actually very limited. It's because once you get the CO2, you will still need a place where you can securely put that for storage over multiple millennia. So that means that in the Philippines, we really need to consider many of the options that have been discussed by my colleagues, those which are relatively highly compatible with agro-industrial systems and those which do not depend on geological reservoirs that we don't have.
Thank you, Academic Shantan. Maybe some inputs from our panelists.
Actually, for the cheapest nets, we have afforestation, reforestation, biochar, and soil carbon sequestration. But one limitation would be their permanence, because afforestation, reforestation has around 80 years of lifespan, meaning after that it stops absorbing carbon dioxide from the atmosphere, unless there's a very good forest management. As for soil carbon sequestration, they found that the lifespan is around 20 years, and there should be a very good management in order to sustain its carbon sequestration potential. For biochar, it's around 500 years. But as for the cheapest options, these ones are the ones that we can immediately implement in the Philippines. And in the near future, I would suggest that we look into enhanced weathering and direct air capture, since these ones have lifespans that are around thousands and hundred thousands of years.
Well, to add to that, I believe that compared to enhanced weathering, biochar can be applied the soonest possible time, as soon as the government decide to implement biochar-based carbon management networks, because biochar application to soil and production utilizes mature technologies. And so the prospect for near-term scale-up, especially in agriculture-intensive economies like the Philippines, is very promising. However, the main technological gap lies really in the capability to predict the actual climate change mitigation benefits. And that's why we really need computer-aided planning, and enabling technologies to acquire real-time data. If there are real-time satellite monitoring of these soils where the biochar is supplied, then we could have feedback or have real-time data which we could utilize to improve the models, to recalculate and then to reoptimize. I think biochar-based carbon management networks can be implemented the moment the government decided to implement this, I think in less than 10 years or 5 years in the Philippine setting.
Thank you.
Hello.
Yes.
Okay, just to add to what everything they say, especially on what Professor Tanab mentioned on the viability of geological sinks in west of the Philippines. Well, actually, one of the identified geological sinks before for the Philippines in terms of for CO2 is the Malampaya. When that reservoir gets depleted it was identified as one of the possible sinks, and there are some studies done in for that, because as far as I remember, the capacity actually is it can store up to 250 megatons of CO2, and one of the insights from that capacity is around 40 to 80 years of CO2 worth of CO2 emissions in Calabarzon area. So what in terms of investments in nets, actually direct air capture might be a good one because of what Riaz mentioned is because of its permanence. But it we just the Philippines would just need a large investment when it comes to DAC and identify or assess the security of the sink so that it would be viable. So, yun.
Thank you, Dr. Tapia. Okay. I have a question here already answered, but maybe we could share this to ignite some discussion. Many developed countries achieve a natural peak after per capita GDP exceeds $20,000, and then start a long plateau period and finally enter the downward channel of carbon emissions. The internal and external environment of developing countries like the Philippines and China is completely different from that of developed countries. Whether the Philippines can learn from the experience of developed countries and form a higher quality carbon emission reduction path than developed countries is very important at present. It involves multiple disciplines of natural sciences and social sciences, and is also an important issue that needs attention in economics, medicine, and human health. Maybe can we get some of the comments from the panelists on this statement? Maybe we could start. Dr. Belmonte first.
Sorry, I did not get the question.
Sorry, it's not actually a question. It's more of what are your thoughts on this statement on whether the Philippines can learn from the experience of developed countries and form a higher quality carbon emission reduction path than developed countries is very important and present. It involves multiple disciplines of natural sciences and social sciences, and is also an important issue that needs attention in economics, medicine, and human health. Maybe you could provide your insights on this statement.
Well, perhaps I actually typed my answer, but just so everyone can hear it. It's definitely true that in any decarbonization roadmap, that we make. For instance, hypothetically, if we were to make a pledge to reach carbon neutrality by the third quarter of the century, so that's any time from 2050 to 2075, again, hypothetically, if that was done, that would be a national multi-generation commitment that will span multiple presidential administrations, but it will be a commitment that will bind generations of Filipinos to change lifestyles basically, and to change the way we do things. So that is definitely something that needs to be examined. Local constraints, cultural aspects need to be part of the planning. But part of the reason we're doing this event today is the discussion needs to begin. One of the panelists presented a slide where 8 out of 10 Southeast Asian countries have already made their pledges. The only ones that have not are, of course, the Philippines and Myanmar for reasons that we can only guess at. But I think the Philippines needs to be in solidarity with the rest of the region and the rest of the world to secure a better future for not just for future citizens of the Philippines, but for the good of humanity. And this it should begin with a top-down policy decision, and the details will follow. And some of the details that we should consider, for example, would be setting up the ecosystem for carbon trading. That includes verification, that includes importing and exporting credits across national boundaries, but that also impacts the scientific community. For instance, it should shape DOST's research priorities. That will, as we know, that cuts across different disciplines. For instance, in an agriculturally oriented or agriculturally strong university like UP Los Baños, there are plenty of opportunities to redirect some of the work that is already being done to further emphasize the potential for carbon sequestration. And that's precisely what I mean by the top-down decision, eventually shaping the details of implementation across different sectors, whether it's for academia, for industry, or for other government agencies. And well, thank you for that comment. I think our intent this morning is really to get the discussion started.
Yeah.
Thank you, Emission. Okay. So I think all of the questions were already answered. So let's move on to the synthesis. Thank you again to our panelists, Engineer Migo Sumagang, Dr. Tapia, Dr. Belmonte, and of course to Academician. To synthesize this discussion, we've highlighted that carbon dioxide removal is needed from the opening remarks of Academician Rasco and the overview of Academician Tan. And of course, to attain the global goal of 2 degrees Celsius, it is imperative that zero net emission must be met by 2050. For the Philippines, this would mean to set carbon neutrality target, optimizing our decarbonization roadmap, as well as optimizing our selection of our entities. And from our panelists, we can clearly see that there is significant research work on mathematical models for biochar-based carbon management network, as well as optimizing our net portfolio. Additionally, the research highlighted existing decision support systems on biochar-based carbon management network and the ranking of nets using nutrosophic data development analysis. Of course, further research work is still there. There are still opportunities for further research work. And from our open forum discussion, we begged the question that if a carbon zero net energy a policy on carbon neutrality is viable, yes, it is viable, and it will invigorate the transition towards adopting net technologies in the country. So thank you again for everyone. Now, we would like to thank our invited guests for this insights and informative discussion. To formally conclude this morning's proceeding, may I now call on Academician Alvin Colaba, member of the Engineering Sciences and Technology Division, Academician Colaba, the virtual floor is now yours.
Okay. Thank you very much, Dr. Ivan Ge. It has really been an enriching morning to everyone. So again, National Scientist Dolores Ramirez, NAST President, Academician Eufemio Rasco Jr., my colleagues in the National Academy, Academicians Raimundo, Maala, Cuevas, and Gregorio, and of course, Academician Raymond Tan. Our focus group discussion today was indeed timely with the recent events that is happening not only in the Philippines but globally. Scientifically, they have been attributed to, to the different changes on our climate and the impacts that is actually a result of this climate change, issues are being felt not only in our country but in the entire world. So this particular forum, as Academician Tan has mentioned, is really trying to bring the discussions, at the national level. And the team of researchers, from LaSalle, from UST, and I'm sure with the collaborations and partnership with the other institutions, will bring together or catalyze the discussions on net zero emissions or net emissions technologies. That is important, for a longer term strategy for the country in cutting greenhouse gas emissions. As pointed out earlier by Academician Tan, we need to have drastic, approaches or technologies that will have to bring down, the emissions in so short a time. Otherwise, we will be overtaken, with the increases of the global greenhouse gas emissions. So on behalf of the National Academy of Science and Technology, Philippines, I would like to express my appreciation to our distinguished resource persons, Dr. Beatriz Belmonte, Dr. John Frederick Tapia, and Engineer Maria Victoria Migo Sumagang for their valuable contributions to this discussion this morning. Of course, our appreciation also goes to Dr. Ivan Ge for moderating and giving the synthesis for this event. The discussion showed us, a new sense of urgency to reduce carbon footprints, and the only way to accomplish this is to embrace, net zero technologies and bring the global emissions into a net zero level. With the latest scientific advances, this will be the first step towards fulfilling our responsibilities as one of the signatory to the Paris Agreement. Before ending these remarks, allow me to recognize, of course, the efforts of Academician Raymond Tan in spearheading this discussion, and I hope that this would not be the last. This should be a sustained one, and perhaps we can bring more, researchers around the country involved in this particular initiative. Together, let us all work hand in hand in creating a healthy and safe environment for everyone and to the society in general. Once again, thank you very much and have a good day. Stay safe and healthy. Thank you.
Thank you very much, Academician Colaba. Before we officially close this event, may I invite our speakers to open their video feed for a quick photo session. Okay. Okay. The NAS Secretariat can kindly give us a cue when taking the picture.
Ano po? 1, 2. Isa pa po. 1, 2. Okay, thank you po.
Sige. Okay, thank you everyone. Congratulations. Bea, Ria.
Thank you. Thank you again for everyone.
Thank you.
Thanks everyone.
Thanks,
Thank you.
everybody.
Ivan, thank you.
Thank
Bye
you,
for now.
everyone. Bye-bye.
Especially to the
Have to
next
move to my
secretariat
next meeting.
for
Bye.
working
Thank
on
you.
this.
Sige.
Thank you.
Let's pursue this, Raymond, in our division. So we'll discuss more about. Thank you guys. I have to go now for my next.
Bye. Goodbye, everyone.
Bye-bye. Bye, everyone. INS Ramirez. Bye-bye.
Recording
stopped.
Then,
Welcome to the Philippine Science Heritage Center's new Salin Lahi Science Center, honoring our top Filipino scientists and their game-changing contributions to the world of science. Know more about all of them and let the Salin Lahi Science Center be your gateway into their minds. Salin Lahi,